Classes in Statistical Mechanics. Lectures by Professor George Phillies, based on his book, Elementary Lectures in Statistical Mechanics, Springer Verlag, 2000. And today, this lecture is Lecture 4, More on the One-Atom Ideal Gas. I'm Professor Phillies, and these are classes in statistical mechanics based on my book, Elementary Lectures in Statistical Mechanics, complete with ideas for the next edition. I suppose there's a message here, which is that we have a very large problem, and we are going to attack the problem one bite at a time. So where we were last time in the book was about page 45, and we had been talking about distribution functions. We discussed the general idea of a reduced distribution function. That is, you have a probability that is a function of several variables, and you add up over some of the variables, and you are left with something that's only a function of the variables that are left. And so what you've done is you've said, I am going to add up over all of the possible states of the system, all the ways this could happen for a particular value of some variable, and I will compare that with other values of the same variable, but in each case, all the other variables I'll add up over. So we'll start with the Maxwell-Boltzmann distribution. And there's a Maxwell-Boltzmann distribution for the momentum, and there's a Maxwell-Boltzmann distribution historically for the velocity. And then there's a distribution for three-dimensional motion, px, py, pz. And then there's a distribution for the speed. How fast is the object going? But we say, yes, the object is going this fast, but we don't care if it's going this way or that way. We add up all over all the directions the object could be going, as long as it's going at the right speed. And to do that, we push ahead and we look at, for example, 4-21, 4-22, 4-23. And what we've said to get to 4-21 is that initially we had a sum over all of the states of the system, which includes all of the positions that are allowed and all of the momenta. However, what happened is we're averaging over functions that do not depend on position. That is, A is only a function of P in 421. The energy is only a function of P, and therefore that integral dx, dy, dz that you have in the sum over states, we can just do. It's the volume V. And that V cancels the identical V in the denominator. So we've just canceled some integrals out to get to 4-21. We canceled the mysterious constant C out, and we actually did the partition function and got 2 pi m kt to the 3/2. That's problem 4-2, which you've done. Now, the next two steps are really simply a change in symbols. And what we say is we will introduce a distribution function for the momentum vector, and that's W sub mb of p. It's defined in 423, and you see in 422 where it gets. And it's the total statistical weight for all of the states of the system in which the particle has momentum vector p. Are there a lot of those states? Oh yes, because the particle could be anywhere in the system, and we added up over the infinitude of possible locations. I then go on, and I will let you read it yourself, that the Maxwell-Boltzmann distribution has a temperature dependence. It has a temperature dependence because you have an exponential e to the minus beta, which is an exponential of 1 over t. And it has a temperature dependence because there's a 1 over t to the 3/2. Now, one way to say I have a temperature dependence, one temptation is to say, oh good, I'll construct a series expansion, a Taylor series expansion. But you cannot do a Taylor series expansion of 4-24, which shows the temperature dependence explicitly. Does anyone see why you can't do a Taylor series expansion of that?
Because if you put t as equal to 0, it explodes on you.
Oh yes. In fact, that's an essential singularity. It's not just a pole. It's not just infinite. It is severely infinite. You can't do a Taylor series expansion. However, you can calculate the behavior of that object as t goes to 0. And so the t to the 3/2 gets big at some speed. But the e to the minus 1 over t, constant over t, goes to 0 very, very hard. And the Maxwell-Boltzmann distribution goes to 0 at 0 temperature. With one exception. If the momentum is 0, then that little constant a in 424, which is, of course, p squared over 2mk sub b, that constant a is identically 0. And if the constant a is identically 0, the exponential is 1 at all temperatures. And thus, in the limit of low temperature, you find that all the particles are sitting stationary. Okay, so we can now push ahead. We discussed equilibrium and non-equilibrium states last time, and we advanced into section 4-5 on reduced distribution functions. And we are going to consider a particular example of a reduced distribution function, and we start at 4-30, which is the ensemble average of some variable a, which is written as a function of r and p. And we'll say, let's suppose a is only a function of momentum, for example, the kinetic energy. In that case, the position integrals in 4-30, page 47, all cancel out. The constants c's in 4-30 cancel out. And if we say, special case, a is only a function of the magnitude of p, so we're going to do 430 for the special case that a of r and p, the quantity we're averaging, doesn't depend on r at all, and only depends on the magnitude of p, we can usefully rewrite the integrals. And we take the integrals dpx, dpy, dpz in 430, and we rewrite them in spherical polar coordinates. And when we do that, we get a dp, d theta to p, d phi p. Those are the angulars. And we get a p squared sine theta. That's just changed to spherical polar coordinates. Now, the integral in 4-31, g, nothing in the integrand depends on phi p at all. The only dependence on theta sub p is that sine of theta p. And therefore, you can do all of the integrals except the remaining integral 0 to infinity dp. And you end up with equation 4-32. And 4-32 is the ensemble average of a if a is only a function of the magnitude of p. Recall, this is still for the one-atom ideal gas, not for anything more complicated. And then I just do a notational rewrite, and I say that the average value of a is the value of a for each value of p, this is in 432, multiplied by the total statistical weight of all of the states that give you p of that magnitude. And what is w prime of p? Why, it's the thing down in 433. And it includes the 2 pi mkt to the 3/2, that's the normalizing factor. It includes a 4 pi p squared that showed up when we changed variables. And it includes the e to the minus beta times the energy. Good. You can, of course, rewrite this from P to V because P equals mv. That's sort of trivial. The other thing you can do is to push ahead to section 4-6. Okay, and in 4-6 we're going to ask, suppose A only depends on position and momentum through the energy. Suppose we want to do the ensemble average of a variable, and the variable is only some function of E itself. In that case, a sensible procedure is to start back a page at 4-32, where we did things only as a function of magnitude P. Why? Because E equals P squared over 2m, yes?
Mm-hmm.
Therefore, anything that is a function of E can equally well be written as a function of P, or vice versa. And so we will do a change of variables from the variable P in 4-32. We skip ahead a page to 4-35, and we replace P with E. And that's what I've done. However, I did it a little carefully. First of all, if E is P squared over 2m, then P is the square root of 2me. That's the equation right below 435, and that's saying that if I know the energy in terms of the momentum, I also know the momentum as a function of the energy. Then what I do is I go into 4-32 and I dutifully do the transformation of variables thing. So in the integrand, wherever there's a P, I replace it with E. The two limits of integration, which were P equals 0 and P equals infinity, I replace with the value of E in those two limits, which happen to be 0 and infinity. Nothing seems to happen. Finally, I am doing a change of variables, and that's shown in 4-35. The numerator in the first fraction is a dE. That's the new integration variable. And the denominator is the Jacobian, because that's how we change variables. Yes? So we did a change of variables, and then you plug in for everything, and you simplify. And when you plug in for everything and simplify, there's a significant amount of trivial cancellation and paying attention to what you're doing. You get 4-36. And 4-36 says the average value of A is, well, we choose A for each value of the energy, and we add up over all energies, and the statistical weight given to each value of E is the x minus beta E. That's the statistical weight of one state having energy E, times sigma of E. Sigma of E is how many states you have with energy E. So if there are 3 states of one energy of E and 6 states of another, sigma of E would be 3 or 6. Actually, sigma of E has been normalized properly. We normalized it properly back in 435, and it stays normalized. And in equation 4-37, I show you sigma of E. Sigma of E is what is called the density of states.
And then I went to the class, and it was reviewed for the
What is the density of states? Well, saying we can count the states of the system is improper because the count of the number of states is continuously infinite. But we can do an integral and find the measure of the number of states within some between two narrow bounds, differentially apart. And then sigma of E is the sum of the statistical weights for all those states in that narrow region of E, except we factor out of sigma E the exponential minus beta E. So sigma of E is large where there are a lot of states and small where there are only a few states. Density of states will show up later. We may not do much with it. It shows up naturally in quantum mechanical calculations, but we're not really going to do that. Okay, so that's the density of states. And having said that we have a density of states and we have a reduced distribution function, we could push on and compare two ensembles which show up much more in other books: the canonical ensemble and the representative ensemble. The comparison happens naturally if you're looking at things that are only functions of the energy. In the canonical ensemble, what is the canonical ensemble? It's a complete, non-repeating list of all the states of the system. Each state shows up once and only once, and then there's a statistical weight for each state, exponential minus beta E. The representative ensemble is different. In the representative ensemble, you don't list every state of the system once and only once. You list a whole bunch of states, and the frequency with which you list states is proportionate to how important they are in the ensemble. In terms of the reduced distribution function of section 4.6, the density of states in the representative ensemble is sigma of E, and the importance of that state is x minus beta E. Good so far?
Mm-hmm.
Okay, so we have now more or less finished Chapter 4. And Chapter 4 we did because it is the simplest imaginable non-quantum canonical ensemble. You can't get any simpler than this. Now we page ahead. And the first page ahead we hit, which I will not do completely, is a side A, the two-atom ideal gas. What is the issue with two atoms rather than one? Is there a lot of new physics involved? Well, frankly, no. You get some new physics when you go to the n-atom system. However, the number of variables that you have to handle to do a canonical ensemble average, if you do the sum over all states, goes from 6 to 12. This is a smaller step than going from 6 to 6 times Avogadro's number. Slightly smaller anyhow. So having said we will take the slightly smaller step, what issues come up? First, we have to be very careful on our notation. We now have two atoms in the system. Each has a position, and the two positions can vary independently. Each has a velocity, and those two velocities, or momenta, are independent. So if we want to generate a list of all of the states of the system, what do? Well, molecule 1 can be anywhere in the volume, and it has coordinates x, y, z. Molecule 2, ditto, it has independent x, y, z coordinates, and therefore we have to label the coordinates. So x, y, z becomes x1, y1, z1, or x2, y2, z2. You have to add an extra subscript identifying which atom you're talking about. Ditto for the two momentum coordinates. The two atoms have two momenta pointing like my fingers in general in two different directions. So this atom has momentum p1, 3 coordinates. This atom has momentum p2, 3 coordinates, and we now need 6 coordinates to specify the momentum of the two atoms. And we do that by adding a subscript 1 or 2. Okay, so that's the coordinate variables. The energy becomes a little more complicated because each atom has its own kinetic energy. So there's a P1 square over 2m for the first atom, and a P2 square over 2m for the second atom.
Are we dealing with atoms of the same mass?
Yes. If we weren't doing that, you would need a 1 over m1 and a 1 over m2. And you can in fact do that, and the notation gets more complicated. But while the notation gets more complicated, there's not a lot of new physics. Why? Well, for starters, you remember we calculated the average kinetic energy of an atom? How does the average kinetic energy, you first, you second, how does the average kinetic energy of an atom depend on its mass?
MV.
No, that's the momentum.
Mhm.
Average kinetic
1/2
energy.
MV squared.
No, I don't want the kinetic energy at one time. I want the average kinetic energy in the ensemble average.
Doesn't
Doesn't.
vary.
It's 3/2 kT, right?
Mm-hmm.
And how does 3/2 kT depend on m?
It doesn't.
It doesn't. You've got it. So the answer is the average energy and the average of the square of the energies does not depend on particle mass. You can find things that do depend on m if you work hard. It's not impossible. Okay, so now we've talked about the energy, and now we ask, well, what does the sum over all states look like? Well, dx1, dy1, dz1, and ditto dx2, dy2, dz2 can each be anywhere in the volume. And a sum over all states puts each of them anywhere in the volume. So how many dimensions of integral do I get as a result of that?
12. 12.
We're just doing x, y, z at the moment.
Oh, 6.
Do I hear 6?
Mm-hmm.
Yes, we get 3 dimensions for each atom. And then the momentum of each atom can vary from plus infinity to minus infinity in each direction. And therefore, we get 3 additional integrals, 3 additional sums over states for each of the 6 momentum coordinates. Gee, I'm up to a 12-dimensional integral now. Okay. And then we chug ahead in the aside, and we calculate the partition function, the sum of the statistical weights of all of the states. The general form is equation A-6 on page 56. And so there's a dpx1 and a dpy1 and a dpz2. There's 6 sums over momentum, 6 sums over position, and then there is the constant in x minus beta e. That's the partition function. That's the denominator. Well, we ask, how can we simplify this thing? First of all, the exponential of the energy, the last term in A-6, the energy can be written as a sum of 6 terms. 1 in P1x squared over 2m, 1 in P1y squared over 2m, and so forth. And therefore, the energy, the statistical weight exponential, can be factored into 6 exponentials. So far, so good?
Mm-hmm.
And once it's factored, each of those exponentials is only a function of one variable. So we can take those exponentials and spread them out over integral signs. And if we look at, for example, integral dpx1, it has attached to it an e to the minus beta p1x squared over 2m. But it has there's no other dependence on p1x anywhere in the system, in the equation. And therefore, we can take those integrals and factor them into 6 integrals. So, we can do those 6 integrals because actually they're the same integrals we did for the one atom ideal gas. It's just we have to do more of them.
Mm-hmm.
So far. And so, if we take equation A-7, which is the same as the original partition function, except I've separated everything out. Each of the terms in square brackets can be done separately, and we end up with a partition function for the 2-atom ideal gas, which is equation A-8. So far, so good.
How would I have two questions? I'm not sure if you want me to bring them up now or when we're done with this.
Go ahead.
Okay. How would we handle the states of the system where the two particles are occupying the same position?
For the particles we're now talking about,
Mm-hmm.
they're point particles.
Okay.
They do not interact, and therefore two of them can occupy the same position. There's no potential energy between them that would exclude this.
Okay. And that kind of rules out my second question of
Which was?
how do we handle interactions between the particles?
That's why you're taking this course, and we will eventually get to those chapters, but we aren't there by a bit yet.
Gotcha.
Okay. Now we could compute the average energy. And if we write out the average energy, and I have done this on a blackboard a few times, we get equation A-9, which needs 3 full lines of the book. Yes?
Oh.
And then we have to be careful. But what we do to be careful is to deal with a form shown in equation A-10. That is, we have a sum of terms, we have a product of terms, and we can split out the sums and the products.
Mm-hmm.
And what equation A-10 shows you is simply the calculus rule that the integral of the sum is
The sum of the integrals.
sum of the integrals.
Mm-hmm.
Well, that's true. In this case, there's slightly more than 2 integrals, namely there are 12 of them. And there's a closing factor which isn't quite as substantial as it used to be, but it's still there. So what we do is we say we will start with A-9. And A-9 has in it a sum of 6 terms corresponding to the energy. That's the thing in square brackets on the third line. And we are going to say that the integral of the sum is the sum of the integrals. And so we take A-9 and we break it into pieces, and we get A-11. And in A-11, I do not write out the 12 integrals 6 times. I use little dots. However, I do write out the lead term, which has an integral over all 6 position coordinates, and 1 P1 square over 2m. And I multiply that into what is going on in the rest of the system. Let me try saying that differently. I apply the integral of the sum is the sum of the integrals. And the bottom of page 57 is the first term of the sum. And then I use some dots to represent the fact that there are 5 more terms in the sum. Okay?
Mm-hmm.
However, each of those terms in the sum is different because it has a different py square over 2m, like p1x square over 2m in its numerator. But they are all the same in that each of them has all 12 integrals. And each of them has e to the exponential to the minus beta e, and the x to the minus beta e includes all 6 energy terms. So when you split up the x to the minus beta e, you get what you see at the bottom of page 57. You get 6 integrals of the form integral from minus infinity to infinity dp exponential minus beta p square over 2m. And one of those terms will contain a p square over 2m. Yes? But there are actually 6 of these terms, and they all have, each of them has all 12 integrals in it. That's where people go wrong. In doing the integral of a sum is the sum of the integrals, or the exponential of a sum is the product of the product of the exponentials. You have to be careful to do those one step at a time so that you get everything properly distributed. Are we good? I have now shown you 2 atoms. Okay, and I am going to give you a homework piece, and it is number 1, except you don't really have to write out all 72 terms if you don't insist on it. You just have to write out enough that I can be sure you knew what you were doing. Writing out 72 12-dimensional integrals, well...
Doesn't sound like a lot of fun.
No. Is it really 72 integrals?
6 times 12.
Yes, because there are 36 in the numerator, and maybe there aren't really 72. Maybe I was fibbing a bit. However, there are 6 integrals for each p squared over 2m in the denominator, or numerator, so there are 36 in the numerator, and the denominator is maybe a little simpler, but there's still at least... Oh, I forgot. Bottom of page 57. That's a 12-dimensional integral. We forgot the integral dx, dy, dz for each atom. We canceled it. So the bottom of 57 actually shows you a 12-dimensional integral, and there are 6 12-dimensional integrals for 72 integrals. That's even before we get to the denominator.
Mm-hmm.
So far, so good. So I have now done the aside.
There are a few friends I kind of want to brag to saying, I'm doing 72-dimensional integrals. Why aren't you?
Well, that's Piker, Mirror, Bagatelle. We will now advance to Chapter 5, and you will do Avogadro's number of integrals with one sweep of the pen.
Oh, even more stuff to brag about.
Yes. Chapter 5 brings us to the n-atom ideal gas. It's centrally important to most of this course because if you want a liquid, you cannot usefully have a one-atom liquid. It doesn't mean anything. You can, however, have a blob of n atoms, and even if n isn't too big, you sort of have a liquid. It may be a very small drop, but it's a liquid. So, having said, we are going to do this. We're going to start out with the n-atom ideal gas, which does not have phases, and we're going to treat the energy and energy square of the n-atom ideal gas. Okay, well, each atom has a position x, y, z, a momentum px, py, pz. We reach in and we say if there are n atoms, we have to put subscripts on all of those momenta so we can tell them apart. And there are n trios, x1, y1, z1, x2, y2, z2, off into the infinite distance, well, not quite infinite, xn, yn, zn. So far, yes? And now I'm sorry, I'm losing my voice. Just a second. So, there are three times Avogadro's number of position coordinates. There are 3 times Avogadro's number of momentum coordinates. And they each have a subscript labeling which atom they're from, and another subscript labeling whether they're x, y, z. Then, in addition, there's the total energy of the system. And writing out the total energy of the system would rapidly become a chore if we had to write out all of the variables.
Cool.
So we cheat. And the first thing we say, this is equation 5-1, is that the kinetic energy of atom 1, that's the left of the equation, it has three components in it because the motion has an x, a y, and a z component. And so we add up the x and y and z components and we get, say, p1 squared over 2m, the kinetic energy of atom 1. For the kinetic energy of all of the atoms, we write down 5-3, that's the statistical weight, and there's a constant c, which we have yet to discuss, and there's an exponential minus beta energy of the system. But the energy of the system is the sum of the kinetic energies of the individual molecules. They have no potential energy interacting with each other, and so it's summation of pi squared over 2m. Okay, now we are going to write out an ensemble average. And you are going to see why this condensed notation is actually useful if you want to get anything done. So what we say is, and this is equation effectively 5-5, where I've written out an ensemble average of some variable a. We sum over all of the states of the system. So we sum over all of the x, y, and z, the possible values of x, y, and z, for each of the n atoms. That, I suspect, would have a decently dramatic effect fairly quickly. Then we sum over the dpx1, dpy1, dpz1. So for each atom, we are summing over 6 coordinates. And for script n atoms, Avogadro's number of atoms, we are summing over Avogadro's number of coordinates. So that's a big summation because you're now getting 6 variables per atom, or 6 times Avogadro's number plus a few per atom. Okay. So go back to 5-5. So we have the sum over all of these things, and then in the numerator, that's line 2, we have the variable being averaged over, which is some value of the positions and momenta, and we have the statistical weight cx minus beta sum pi squared over 2m. So we have 2 parts. And, oh my, and then we have a denominator as well as a numerator. And in order to write that down, we need to leave out a few terms like Avogadro's number minus 12, or we'd never finish writing it out. Okay. Then we do a few things to check, for example, that the systems do not have moment. I'm not saying that very well. Let me start again. We've got the ensemble average. It has a numerator and a denominator. And we can write out the average, and we effectively do that in 5-6. And in 5-6, you have a numerator, which has the quantity A being averaged over, and the statistical weight. And we have the denominator, which is the partition function. And the partition function is now bigger than it used to be, but it's really just more of the same. Okay, let's do the partition function first. That's 5-7. And in 5-7, you have a sum over all of the states of the system. And it is many-fold infinite. And that's the thing being integrated over is the statistical weight of the state. So you find the statistical weight of each state, and you sum over all the states. Ooh, Except how do we handle that exponential? We use the rule that the exponential of the sum is the product of the exponentials. And if you look hard at the line above 5, 8, there is a mistake. That should be a times sign, not a plus sign. So exponential of a times b, exponential of a plus b is exponential of a times exponential of b.
Mm-hmm.
And in particular in 5-8, the exponential of the very large sum is the product of the exponentials. Well, once we have the exponentials broken up into a product, each of those exponentials separately only depends on one variable.
Like gasp.
Yes. And so we can take the exponentials and distribute them across integral dp1, dp2, dpn, and we get almost to equation 5.9. Till we get to equation 5.9, we have to do one more thing. Look back at 5-7. We're adding up integral dr1, dr2, but what is integral dr1 over the volume V? You've done it many times already.
Volume?
It's on the 4.
Yes.
No, it's the volume.
Yeah.
We're just doing the integral dr1. So over the integrals over the n volume vectors give us the volume to the capital N power.
Mm-hmm.
Mm-hmm.
And then when we spread the exponentials over the momentum integrals, we get those things in square brackets in 5.9.
Mm-hmm.
However, because each of those integrals only depends on one momentum variable, we can separate the integrals completely into a product of well, they're really three-dimensional integrals. Three-dimensional integrals which, 5.10, you know how to do.
Mm-hmm.
Yes? And so, we take the three-dimensional, we plug everything in, and we get 5-11, which is the partition function for the n-atom ideal gas.
Okay.
And it looks a lot like the partition function for the one-atom ideal gas, repeated capital N times. There is still this constant script C in front. I'm going to emphasize at this point, script C is not the same each time. Script C, when we talk about it, depends on how many atoms there are in the system.
Mm-hmm.
And so it'll keep changing in value, but we write it as script C.
Because it's a constant.
It is a numerical constant, and it is part of the statistical weight. And if we're doing an ensemble average, it is always the same constant above and below. And since it's the same constant above and below, what does it do?
Cancel.
Yes. Okay. I shall, however, make a minor aside.
Mm-hmm.
I have ignored the atom wall potential. The atoms do not interact with each other, but they might interact with the wall of the system. Now, ordinarily, in the range of interatomic interactions is tens of angstroms or hundreds of angstroms, very small distance. The room is meters across. So almost none of the volume of the room is close to the wall, and therefore the contribution of the atom wall potential to the problem looks like it can be ignored. And if the wall is simply a hard surface and nothing else, it can be ignored. You just have to be careful when you're specifying exactly where the wall is. The wall is at such a location. Here's the atom coming in, my fist. Here's a wall. The atom contacts the wall, and the edge of the system, as far as the atom is concerned, is not here. It's at the middle of the atom when it's in contact with the wall. The atom has a distance of closest approach to the wall if you tried measuring the location of the wall with an interferometer. Is that possible? Yeah, sure. What you would have called my MQP advisor did an interferometric measurement on one occasion, and it was accurate to 10 to the minus 6 fringes, which translates to about 1,000th of an atomic diameter. Now, that was the low-grade measurement. His modern measurement, it's called LIGO, the Large Interferometric Gravitational Observatory, is trying to make distance changes measurements, and you're trying to see changes in distance of a part in 10 to the minus 19. This requires a little thought, but it's been built. Okay, so we've talked about the partition function.
Now, going back to the first question I had earlier, what happens when the two particles are in the same spot? With the n number of particles, there is a state where all the particles occupy the same spot. Is that just so improbable that we can just throw it out?
The particles do not interact with each other. Mm-hmm. So they can all occupy the same space at once. They're allowed to do that.
Okay.
Yes. If we had interacting particles, the answer would be, if the particles interact, there's a potential energy, yes?
Mm-hmm.
And so the statistical weight includes a term, e to the minus beta, potential energy. And as I bring the two atoms closer together, remembering the potential energy is repulsive, what happens to exponential minus beta u?
Increases.
U increases. U
Yes.
gets very large and positive.
It gets smaller because it's a negative.
Yes, exponential minus beta u goes to 0. So the states in which the particles are inside each other have statistical weight 0.
Okay.
And that's taken care of by the potential energy.
That makes sense.
Yes. Let me suggest a simple problem that will show the same effect. We are now in an ensemble in which the atom can be anywhere in the universe. But the potential energy of the atom, if it is not inside this box of volume V, is plus infinity. What happens to the partition function when we look at this new problem?
Goes to 0.
Well, no, there's still states where the atom's inside.
Yeah.
The answer is it's the same partition function than it was before. Integral dx, dy, dz now go minus infinity to infinity, but for all the states out here, the statistical weight is 0, and so the partition function is the same as it was before.
Okay. Yeah.
Okay, we now chug ahead, and we now get to section 5.2. And I am going to tell you what happens in 5.2, but we certainly are not going to do it this time. We are going to calculate the average value of the energy and the average value of the square of the energy.
Mm-hmm.
Okay, the energy is, it's implicitly written out in equation 5.13. It's summation I equal 1 to n, pi square over 2m. Yes?
Mm-hmm.
Now, each of those pi square over 2m's is really 3 terms, because there's a p1x square over 2m and a p1y square over 2m and a p1z square over 2m. So the energy, written as p square over 2m, is a sum of 3 times n terms, which are all the same as except for labels. Also, the square of energy, E square, is 3n times 3n, or 9n squared terms. And the 9n squared terms, well, you could say they're all the same except for labels. But some of them have, the two terms have the same label, and some of them, the two terms, have different labels. That if you're taking a product of a plus b times c times a plus b times c, there are a square terms and there are A, B terms. The A square terms, the two parts of the product are the same. The A, B terms, the two parts of the product are different. So we are going to calculate the average energy. And basically it's done using exactly the same steps as before, but there's a little more work involved. What is the work involved? Well, let's see. I imagine it's problem 5.3 and problem 5.4. That's for E square. And maybe you should also show that equation 515 follows from equation 5.14. So you're going to actually do the step to get you from 514 to 515. You're going to do the step to get you from, it's in the homework, 521 to 522. You're going to do the steps needed to get from 5.23 to 5.24. And finally, you're going to verify equations through 5.29. Okay? Now, where do people go wrong on this? Well, let's look at 514 just for a second. In 514, you have a summation I equal 1 to n, and what you are summing over is terms in which there is a pi square over 2m outside the exponential, as well as the e to the minus beta pi square over 2m. This is just writing out equation 5.13. Equation 5.13 is what you're going to evaluate. And what people forget is that when they expand the sum I equal 1 to n in the main line, the same exponential, the exponential of the sum, gets carried along. And so each term, like p1 square over 2m, has an exponential minus beta summation j equal 1 to n pj square over 2m. So the big exponential gets distributed out. And then in separate steps, you can spread the exponential of the sum is the sum of the exponentials. You can spread that over all of the integral dp's. And if you do that carefully, you will get all these results. If you do it less carefully, you will not get these results, and you will get something that is wrong. However, if you're careful, you'll get it to work. Oh, what else could you do? For the things I just described are due Monday. And then for Wednesday, do 5.6 and 5.7.